Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Formal good evening to you all, grade 10s. Thank you so much for joining me tonight. We're going to look at the topic wave sound and light, and some students have covered quite a bit through it. And what we do, we're just going to knock through some maybe revision and lay some foundations for it, and then we'll take it from there. Okay, so there is such a thing, before we get into the waves and different types of waves, as something that's called transverse pulses. Okay, so transverse pulses, we're going to look at transverse pulses on a string or spring. I'm going to have a look at something called pulse and amplitude. Okay, there's some terms, of course, that we need to get used to. Okay, when we do this little section, okay, term called medium. Okay, of course, you're going to need to go through what is a pulse. That's broken up into two things. We've got amplitude, and we've got, of course, something called pulse length. Okay, and of course we've got to go through something called equilibrium position. And then another term is, of course, what a transverse pulse actually is. Okay, which we'll go through first, actually. So a transverse pulse, maybe I'll try to take the definition from up top here. Okay, first of all, it is a pulse in which the particles of the medium, which we will go through, of course, what the medium obviously means, okay, move at right angles to the direction of propagation of the pulse. Okay, so that is a transverse pulse. Okay, now when we mention the medium, all right, what we mean by that? Okay, now a medium is a material, all right, it's a piece of material, okay, but the material through which a pulse or wave travels, all right. Another word for travels, of course, is propagated, okay. Another word for that is also transmitted. Okay, so material could be, example, like I said, string, slinky, which is what was used at schools when I was at school. Slinky spring could be water, or of course air. All right. Now a pulse, another thing that's known as a pulse, or a definition for a pulse, of course, is or one pulse would be what is known as a single disturbance. Okay, you can actually see the disturbance happening when you flick the string or something, or even a rope. You know, if you have a little rope, like, you know, those ropes that they use for training, where you just got to keep going with those little CrossFit guys. That's what they use it for, of course, to create some muscle on the shoulders and the arms, and etc., etc. Okay, of course, you see quite a few disturbances by if you increase the speed at which they go at. Now, of course, that pulse has two things: amplitude and pulse length. Okay, now amplitude of a pulse is the maximum displacement of a particle of the medium from its equilibrium or rest position. So if you must draw it, which I will in a second, I'll show you what the amplitude is, and a pulse length is obviously the distance between two ends of a pulse. Okay, and then equilibrium position is when there'll obviously be a rest position. Equilibrium position where the medium is at rest. Okay, so if we have a look at an example of how it looks, example depiction. So let's say we got a pulse here. Maybe we'll say this is like a slinky. Okay, I can't draw a slinky because it's going to be completely. I'm just going to draw it's in a using some straight lines. Maybe use another color. So there you go. There's Slinky, and then boom. There's a little bit of a disturbance here, and then it levels out again. Okay. So first things first. Okay. This little, gonna draw a little. Well, that's gray and not white. Let me get the white color there, so you can the clear color, so you can see this little thing over here from this point up until this point here. Okay, we just increase this a little bit, this length. Okay, this is called the equilibrium position. Okay, and that I think my nib is too thick. Let me bring it down here. Okay, it's the equilibrium position. Okay, right here. Okay, then obviously from here to here, so I'm going to take do some color drawing here. Let me just increase the size there. Okay. Okay, very bad drawing. Here we go. Okay, from there to there is what's known as pulse length. Okay, that's pulse length. And of course, this little height that's over here, okay, that'll be known as amplitude. Okay, this little distance here is known as the amplitude, okay, of a pulse. Alright. Alright, now there's another term called interference, and also another term called superposition. Okay. However, the interference is broken up into two different types. Okay, there's such a thing as called constructive and destructive. Okay. Now interference is the phenomenon. Okay. Interference only occurs, okay, when two pulses meet as they move. Okay, but not just as they move, but as they move through the same medium. Now, interesting to note, like I said, we've got two different types. Okay, so let's start with the first one. Let's start with constructive interference. Okay, now constructive interference, okay, this occurs, okay, when two pulses or when pulses overlap. Okay, so they overlap, and the resultant, okay, the resultant displacement where is it? The displacement of the medium increases. Okay, it increases at the point of overlaps. In other words, it makes a bigger pulse. Okay, it makes a bigger pulse. Okay, so when the two meet, it obviously yields a larger pulse, or with an increased amplitude. And then of course we get something that's called destructive. So I think it's easy to remember it like this. Constructive creates, it's constructive. If something you are constructive, it's good. It's positive. Destructive, obviously it's bad. Okay. Now with destructive interference, okay, this occurs of course when pulses, okay, let's write that down first. When the pulses with displacements in opposite directions, alright, result in the resultant displacement decreasing rather than increasing, as opposed to as in the constructive. Okay, constructive, they meet, makes a bigger one, and then they separate again. That's constructive interference. Of course, if they're in opposite directions, okay, one pulse coming from the bottom maybe and another one coming from top, okay, they meet, smaller displacements before carrying on. Okay, that will be an example. Okay. So what we have here is a graphical representation of constructive interference. Sorry. So what happens is, of course, you got two pulses moving along the same medium, and they're going, obviously one's going to the right, the other one's going to the left, and they meet in the middle, and of course they create one big pulse. Eventually they will separate, so B of course will be over here on the other side, whilst A will obviously be on this side over here, carrying on at the same amplitude that it is. So that's constructive interference. In other words, it creates a bigger, so this displacement here is larger than either one of these two individually. Alright, what we got here is destructive interference. So of course we see we got X and Y, or negative X because it's obviously going at the bottom, is going in opposite directions here. This one is obviously at the bottom, difference to Y, which is on top there, and they're going to obviously meet in the middle. As a result of when they do so, we've got obviously Y on top here. So you go Y, and this is still negative X. But this purple little legend that I've created here, I didn't want to leave it without the arrow, because it would look like it would been a minus outside of a bracket. Okay, but this little purple color here, which we've drawn in here, not the best, I might have you, but still to make a point nonetheless, it's the result of negative X, of course, plus Y, which yields, of course, a lower or decreased displacement of the medium at the point at which they overlap before they do obviously carry on in their respective directions. Alright, two different types of waves that we get in wave sound light is transverse waves, and then we also get longitudinal waves. Longitudinal waves, sorry. Okay, so a transverse wave, alright? A transverse wave is a succession of transverse pulses. Now, what a succession of transverse pulses basically means like this. They follow on from each other. Okay? There's a poor but graphic representation nonetheless of a succession of transverse pulses. Okay? Now, a more formal definition, it is a wave in which movement or the movement of the particles of the medium is perpendicular okay, it's perpendicular. We all know what perpendicular means, which is at 90 degrees to the direction of in the direction of, or let's say in the direction in which the wave moves. Okay, that's it. All right. So, a couple of things just worthy of mentioning. Okay, is something that's known as a mechanical wave. All right. Now, mechanical wave propagates through a medium and is generated by a regular to and fro movement. Okay. So, if you are standing on the opposite end of a slinky or whatever, and you actually invoke a movement, okay, or you're moving it to and fro, of course, that creates a certain type of it's called a mechanical wave. Okay. In other words, it transfers energy from the source of the wave to other locations. Alright, so in other words, the source would be obviously you causing that movement, so I would be the source or you would be the source. Okay. There are a couple of key points of a transverse wave is, of course, a couple of more terms known as a crest. Okay, now a crest of the wave would be this little point here in yellow. These will all be crests. Okay, the top end, okay, of the amplitude. Well, amplitude is for the opposite as well. Okay, which is basically the point that is maximum. Fix this. Couldn't even spell right. Okay. Now, a crest is obviously the maximum positive or upward displacement or position. Okay. And then you get something else which is called, I didn't really call it a trough. Okay, which is the minimum. Right? And a trough is obviously the, sorry, not the minimum. It's actually the maximum negative position. So basically it's the opposite of a crest, just the negative, because it's the downward position. Okay. Then you get something that's called a wavelength. Okay, now wavelength, which obviously is quite intuitive, not going to really give you the definition for it because it's the length of the wave itself. Okay, but it's basically measured in the Greek symbol called lambda. Okay, now how you calculate wavelength though is calculated taking the distance between. Okay, it's the distance between successive, again that word succession or successive, crests or troughs. Okay, which we'll look at in an example. Okay, which will obviously complete the wave. So from crest to crest or trough to trough would be one wave. Alright, or that would be the length of the wave. Okay. That would be the length of the wave, especially if there's a succession of it. Alright. Okay. Now, the wavelength equals the displacement between, like I said, successive crests or successive troughs. Okay, but then we get something else that's called period, and there's something else that's called frequency. Now, the period and frequency, that's probably the most important thing when it comes to transverse waves. Okay. By the way, these are troughs over here on these succession, these little low points here in red. Frequency and period, they actually come into play because that's where the calculations for this section start coming in, because it's nice and well that we know all these lovely terms and everything, because you know terms are important, knowing terms and everything. Yeah, we can answer one word questions in the exam. We can answer those 1 mark or 2 mark questions with naming these little points in an exam question or test question. But if we need to calculate, obviously one of the things that we're going to need to calculate, period, frequency, or even lambda, which is wavelength. Okay, so when we talk about the period of a wave, okay, a period is similar to time because it is measured in seconds. Okay, now the period of a wave is also known by capital T. Okay, and the formula for the period of a wave is given by T is equal to 1 over the frequency of a wave. But the definition for it though is the time taken for one wave to pass. Okay, it's the time taken, all right, for one wave to pass a complete point. Now, another way for saying that, it is the time taken for one wave to complete itself. All right. So it's the time taken, again, for a single complete wave to pass a fixed point or to pass a complete point, okay? And we measure it in seconds. Okay, so let's actually add that in here. It's measured in seconds. Of course, it's just a little s. Okay. Then we get, of course, to the frequency of a wave, okay, which is given by the opposite of this. The frequency of a wave is 1 over the period, 1 over t. Now, frequency of a wave is the number of complete waveforms to pass a point. Okay, the number, now we're concerned with the number of complete waveforms or complete waves. to pass a fixed point each second. Alright, got that definition down, took a while, okay? And we measure frequency in hertz, okay? So, measured in hertz, I think you spell it, well, that's the unit for it, it's H-E-R-T-Z, H-E-R-T-Z, yes, hertz. Okay, H-Z, okay, that's the way we write it in, okay, cool. And that's the calculations, of course, that we need for, well, to two calculations, but of course we are able to also calculate, of course, the velocity of a wave or the wave speed, okay, which actually has to do with frequency, okay, because we get such a thing as points that are in phase and points that are out of phase, all right? Points that are in phase would be like crest and crest. They are in the same phase, but crest and trough, they are out of phase, okay, for example, okay. So A and F would be obviously in phase. Sorry, not A and F, sorry. If I have to draw points on a graph, let me rather just do that. I don't know why I said A and F. Let me just draw points on a graph quickly so I can show you guys what I mean. Let's just draw maybe a straight line here quickly so I can use this as my measuring point. So let's draw here, let's draw there, let's come up here. Sorry, let's do it again. Let's draw here, let's come up here, let's come up here, let's come up here, and let's go here. Okay, so we've got two troughs and two crests. Okay, so let's say, of course, this point here, this point A, then we maybe got another point here, maybe that's point B, and then we got this point here, which is point C. And then we got point here, we got D, maybe another point here, it's E, and up top here we got F. Okay, we can name the points as we go there. So A and F, they would definitely look like they are in phase. Okay, they are in phase. Okay, but for example, A and F would be in phase, but A and D are out of phase. Right? They are definitely out of phase. They're not in the same phase. Or if we carried on here, so we got F there, we got G, and we got H. Okay, so one full wave would be from C to H because you got all the way from here down and up there. Okay, and then obviously from H onwards would be the new wave. All right, so we actually got 1, 2, that's one wave, and then here would obviously be the other half of it. Okay, but even A and H, for example, they are out of phase. All right, they're completely out of phase. Completely. All right, completely. Not in phase at all. Okay. But what happens, of course, we remember we can work out the period, we can work out the frequency, we can whatever. But what happens if you want to calculate V, which is wave speed? Okay. So what happens if you want to calculate wave speed? Now there's a formula for wave speed, of course, which is it's obviously measuring the speed of the wave in meters per second. It's calculated by the formula V is equal to F times lambda. F times lambda, so it's the product of the frequency times the wavelength. Okay, and one thing I didn't mention is that the wavelength is measured in meters. Okay, the wavelength is measured in meters. Okay, that's the unit of measurement for wavelength, is measured in meters. All right, and that's how we calculate that. It's a very simple formula, of course, and we'll do a little example of it as well, just to make sure that we can actually get these types of calculation questions correct. Okay. Now, since the speed of a wave in a given medium is constant, okay, sometimes a speed of a wave will be given to you as a constant, okay. You can also calculate the speed of a wave using the other formula, or another formula called VAV is equal to the change in displacement over the change in time. We've probably all seen this where we did mechanics before, where delta x would be the displacement, okay, which obviously we know is the difference in position in meters of a point on the wave For example, that's either a crest or trough, and time would be seconds, of course, for how long it obviously takes for that to complete. And we'll just use the time point that is on the graph. Most of the time, this formula is sufficient or suffice, of course, because we can calculate the, remember the period is, of course, how many waves or the time it takes for one complete wave to pass a point. So how long it takes for one complete wave to actually pass. And if you can read that off a graph, 1 over the period will give you the frequency. And once you got the frequency, of course, you can obviously calculate the wavelength and then calculate the wave speed. So this is usually suffice. I do not recall using this formula when I was doing this section. But that was, again, that was about, well, this is grade 10, so 10 years ago. It's actually 10 years ago, so I can't recall that well. Okay, now longitudinal waves is the other type of waves. Okay, they also come on a spring as well. Okay, but longitudinal waves, first of all, it is a wave. Okay, in which the movement of particles of the medium is parallel. Okay, in other words, forward and backward. To the direction in which the wave travels. Now, there's not much we can do with longitudinal wave, okay? As a transverse wave, we've seen how that looks, but I can show you how a longitudinal wave would be depicted, okay? A longitudinal wave would be depicted much like this. Okay, very low amplitudes, low troughs, more like long, of course, part of the wave, whereas a transverse wave would obviously go a bit more up and down, of course. There's not much or many calculations that we can perform with longitudinal waves, but this is how we would recognize a longitudinal wave if it were drawn in a graph versus a transverse wave, where we can see it's got better or more increased troughs or increased crests, of course, in their nature. Alright, so that's about it that we need to know or can grasp from longitudinal waves. Wavelength and everything will work the same in terms of calculation and everything like that. The calculations would, of course, stay the same. Thank you, grade 10s, for joining me this evening for our session. We will see you all in the next one when we continue with sound waves.